So, welcome back to the second part on this presentation on the general derivatives. In the last part, we wrote down all of the rules of differentiation in one convenient place, and then we used the rules to differentiate this function over here. We then remarked that doing it this way was way too complicated, and I promised that I'd show you an easier way. Now, I very highly doubt that I'm the first to come up with this. I'm sure many people have come up with it in the past. But basically what I do is I represent functions with boxes. And then the derivatives of those functions, we're going to represent them with checky boxes. And then if we do that, we can actually go ahead and rewrite all of these rules that used to confuse me in, I think, a much more friendly way. Okay, so for the superposition rule, I've just gone ahead and replaced h of x for a square, f of x for a circle, and g of x for this diamond-like shape. Now the superposition rule just ends up replacing all the functions for their derivatives, and that's exactly what I've done over here. Okay, so next I can just go ahead and do the exact same thing for the product rule, replacing h, f, and g for the same shapes. So again, the visual is actually pretty clear. The square is just equal to the circle times this diamond-like shape. And that means the square derivative, or the checky square, is equal to the derivative of the first, leave the second, leave the first, then differentiate the second. So for the superposition and the product rule, I don't actually think this notation adds very much. But where it really shines is actually when we apply it to the chain rule. The way we write maths today allows us to actually write a function inside of another function like this. By representing the functions as shapes, you can actually nest the shapes in a pattern that looks exactly like this. Okay, so here we have this square and it's equal to some function with another function nested inside of it. Now the way we actually differentiate the square is we differentiate the outer function with respect to the inner function, and then we multiply by the derivative of the inside. This idea of differentiating some function and then unpacking its inner function and then differentiating it kind of reminds me of those Russian dolls. It's kind of like having a smaller doll inside of a larger doll and then being able to lift the larger doll to expose the smaller doll. And indeed, this actually continues to work if you have more than two nested functions, which I give an example of in my video on the chain rule. And then for the last rule, the quotient rule, we can also rewrite it in the exact same way. So let me go ahead and just do that. So just in case you missed the quotient rule, the derivative of some function divided by another function is equal to the derivative of the top times the bottom minus the top times the derivative of the bottom, and then you just square the bottom and put it on the denominator. Now, of course, I should give you an equally difficult problem to actually solve using this box method, and it turns out that you actually never really need these if you get really good at using these boxes over here. Okay, so now I'd like to show you how I'd actually use something like this to differentiate something even more complicated than the example I gave you before. If you actually get good at using this method, you can more or less learn to differentiate almost in your head. Okay, so without further ado, let's go ahead and actually write down another example. Okay, so I've chosen an equally difficult example function here, and we'd like to differentiate it. Now the first thing I'm going to do is I'm going to copy it to a new line. Okay, so the first port of call is to actually draw shapes around every function that I already know that I can differentiate. Okay, and now if I actually covered up some of these functions, you'd notice that you actually have another box around them. And the same goes for this one over here. Okay, so the shapes you draw don't really matter, but they should at least be easily identifiable to you. Now technically, the product of these two terms could also have a box around it as well, but I tend to leave off boxes like those ones. Okay, so now I'm just going to go ahead and apply these rules over here directly to these shapes here. First, we're going to go ahead and draw the checky box of this square. And now after this, on the highest level, we notice that we have a superposition rule. So we're going to go ahead and differentiate the first box, but then we're going to deal with the second box afterwards. Okay, so now that I have two shapes that are touching each other, I immediately know that I have to apply the product rule. However, because I have nested shapes over here, we also have to unpack the nested shapes using the chain rule as we go. Okay, so the first thing I want is the derivative of this first term. So let me go ahead and unpack that first. And then after this, as you can see by the product rule, we just leave the second term intact. So we copy this term down here. Okay, so now we've actually gone ahead and done the first half of the product rule, But then we also have to do the second half of the product rule, where we differentiate the second term. So for starters, we're going to write the first term as it is. So let's copy this term over here. And then immediately after that, we just have to differentiate the second term, which will involve a chain rule when we try to unpack this. Now, one thing you do have to be a little bit careful of is this minus sign over here. Since we have a product rule over here, we have to remember to put the minus sign out the front and put brackets on the function over here. Okay, so now that we've actually written out the derivative in terms of all of these shapes, we can just plug in all the different derivatives that we know how to find. Okay, so the derivative of h of x is just h dash x. Now we just want the derivative of this circle, so we just want the derivative of 2x to the 7, which is 14x to the 6. Okay, now to differentiate this part over here, we just want the derivative of the outer shape in terms of the inner shape. So we're just going to go ahead and cover the inner shape and say, what is something to the power of 5 differentiated? And of course, that's going to be 5 times something to the power of 4. So now that we've differentiated the outside, we unpack it, and then we just copy the inside in. And then to get this term over here, we just have to differentiate the inside, which of course, the derivative of 2x squared plus 4 is just going to be 4x to the power of 1. The 4 just goes away because it's a constant. Now the next thing to do is to just copy out the second term as it is. So we're going to copy this whole term into here. And now again, we just want this term. So we're just going to copy it directly from here into here. Okay, so for the final term, we want the derivative of this six-sided shape in terms of the inner shape. So let's go ahead and cover up the inner shape and ask what's the derivative of a square root. As we already said, the derivative of a square root is just 1 on 2 times the square root of whatever we had on the inside. Again, the inside isn't differentiated, so we just copy it exactly as it is. But then finally, we do actually want to differentiate it by unpacking it, so we put its derivative over here. The derivative of 3 minus 4x to the power of 3 is just the same thing as minus 12x to the power of 2. Okay, and this actually completes our derivative. The derivative of this function over here is this giant function over here. This kind of just brings me to this cautionary tale of mine. You can kind of see that this function is already pretty bad, but its derivative is absolutely atrocious. I mean, when would you ever want to use a function that looks like this? So the idea here is, just because we can go from here directly to here, doesn't mean we always should. Sometimes doing a little bit of work before differentiating is actually very, very helpful. So to show you this, let me just go ahead and show you one last example. Okay, so here's another function that we actually might want to differentiate. So we could just start off by drawing boxes around all the relevant parts. Okay, so what do we got here? We've got a product rule on the outside, and then we've got a quotient rule on the inside, and then we've got a chain rule inside the quotient rule. This looks like an absolute mess, and I don't really want to attempt it. And I'd kind of say this in the following way. Don't ever brute force unless you really have to. So instead, what we're going to do is we're going to expand these brackets, and then once you do that, you'll end up with a much simpler expression to differentiate. Okay, so now, after we've expanded, we actually already have a much simpler expression to deal with, but we can take it even further. Notice that this x crosses out with this squared. And on top of that, you can actually join these two terms together to make something even simpler. Okay, so now this function up here and this function down here must be identical, because we just simplified the top function to get to the second function. And if we actually go ahead and draw boxes around this new function, we'll notice that it's actually a fair bit easier to compute. Note that it's also possible for this 2 to come out of the denominator and go below the 5 to give us a constant of 5 on 2. Okay, so let's look at this a little bit more closely. Notice that because we expanded out the product over here, we don't have to perform a product rule on the final result. Because we didn't really do too much to this term or to this term over here, we still have this quotient rule with the nested chain rule, but the lack of the product rule makes this so much easier to compute. So let me go ahead and find it just by actually writing everything out in terms of the boxes. Okay, so let's make sure that all of this makes sense. H of x differentiates to h dash x, and that means that this square turns into this checky square. Okay, so now we're going to have to deal with this quotient over here. The first thing we're going to do is we're going to differentiate the top, but when we do that, we have to unpack its inside, and then we just leave the bottom alone. After this, we're going to leave the top alone, and then we're going to differentiate the bottom, and then after all of this, we're going to just square the bottom. Okay, so let's just go ahead and fill out all the derivatives we know. First off, the derivative of 20x to the power of 3 is just going to be 60x to the power of 2. Okay, so now to differentiate this term over here, we just have to cover up the inside and differentiate the outside. So something to the power of 2 just differentiates to 2 times something to the power of 1. Okay, so now after this we have to differentiate the inside and put it over here. But the derivative of x plus 1 is just the same thing as 1, so we can just write 1 in that box. Next we're going to copy out this circle. Since the circle contains x, we just copy x over here. Now after this we remember this minus sign, but then we also just copy the top exactly as it is into here. And now we just go ahead and differentiate this x over here and put its derivative right here. Now the derivative of x is of course just 1. Okay, once all of this is said and done, we just copy the bottom into the bottom and square it. So we're just going to put x squared on the denominator. Now what I'd do at this stage is I'd just go ahead and rub out all of the boxes so we can see the final derivative. Now if I wanted to, I could go ahead and simplify this expression here, but that's not actually the point of what I'm trying to show you. The main takeaway here is that just because you can differentiate something straight away, it doesn't mean you necessarily should. You might actually create a lot more work for yourself than you really want to. However, if we actually simplify the expression first before taking its derivative, we can actually make the process of differentiating much simpler for ourselves. And now, I've actually completed all of the examples that I wanted to show you. Okay, so now I'd just like to summarize before I leave you again. This lesson was meant to help you consolidate all of the different rules that we've learned about differentiation. Initially, we wrote out all the rules that can help you differentiate a general pair of functions. And then we talked about the derivatives of some specific functions, including monomials and square roots. We also alluded to the fact that if you keep studying mathematics, you're definitely going to see way more functions appearing on this list. And then finally, I showed you my box notation for these original functions over here. So just a quick note here. It's really up to you whether you prefer to use this shape method over here, or you prefer to use the general functions instead. Both methods, if applied correctly, should give you the exact same derivative, because after all, they're just rewrites of each other. However, in all honesty, because it is a little bit tricky to actually get used to these rules over here, it's probably best to start off with these until you become comfortable with these ones over here. Of course, you are going to do a lot more writing up front, but when you do get used to it, you can actually transition to these ones over here. And with this, we've actually completed our discussion on the general derivatives.